Here we have some data, a histogram, and we're trying to figure out whether they're normally distributed. So what do we do? Well, we know the normal PDF. So let's see. My drawing skills are not remarkable, but I'm going to try to draw the normal PDF. And going down, trying to be symmetric. Okay. So, is that a good fit for the normal PDF? Well, we know here is a little bit, data missing or relative to the curve. And maybe here, there's a little more. Here, there's nothing down here. Well, if you can tell me whether this is a good fit, that's good for you. I cannot. So, the problem is that humans are not very good at deciding whether something follows a curve. And the Gaussian density is a curve, not a straight line. Humans are much better at judging whether something is on a straight line. So the idea for diagnostic plot 3, figure out whether something is Gaussian, is to transform the data, specifically the residuals, the data and then to give the residuals, to yield a straight line if the assumptions of normality is true. Okay, so here we have a PDF. We know cumulatively the probability must be 1, right? The probability sums to 1. And just as an example, I'm considering just 5 observations. And so I'm dividing this probability mass region into 5 equal-sized bins. 5 observations, so each of these bins has probability mass of 0.2. And then if the data are normally distributed, then I know that the points must roughly 1 point be in each bin, if it's normally distributed, very roughly. Now, we're going to pick 1 point representative of the bin, and the most obvious one to pick is the median inside of the bin. By median, I mean this ends at 0.2 probability mass, cumulative probability, so the median between 0 and 0.2 is 0.1 probability mass, and between 2.2 and 0.4 is 0.3, and so forth, right? So, and given, if we know that this is a normal 0-1 distribution, then we can actually compute the quantiles. I'm getting a little ahead of myself. So here I'm just saying that I'm looking for a quantile that corresponds to the cumulative probability 0.10 here 0.3, 0.5, 0.7, 0.9. That's what we had on the previous graph. Okay, so I know which points I have of the cumulative probability. And so because I also know the equation for the normal density, Gaussian density, I can figure out the quantiles, right? Such that there is below whatever value, the quantile, there's 10% probability. And then we can figure out that for the 10%, the first quantile, based on this observation, is 1.28, minus 1.28. So here, yeah? So, and I can do that for all 5 points. And then I can say, well, if I now plot the quantiles that I just found out, minus 1.28 and so forth, with the actual y values, then those should be the same, which is another way of saying they should be on a straight line. Right? They should be on y equals x. These are only 5 points. With few points, there's a lot of variation. So this is a sample from a normal distribution. And this is something that is very common, so it's not unusual in any way. What you see here, the 5 dots, is a straight line. If you haven't seen plots like this before, then that sounds strange. Remember, there's variability because it's few points. This is completely consistent with a straight line. All right. So that was an example with just 5 points. Of course, usually we have more than 5 points. And yeah, here's some code of how I did this. And the other thing is, we said it's normally distributed 0, 1, but in general, we are interested in normally distributed mu sigma. But that's easy to fix because we just subtract the mu and divide by the sigma. Then we get standardized variables, and the standardized variable has a distribution of normal 0, 1. And then we are back to what we know, right? What we know with 5 points at least. Well, when we had 5 points, we said the cumulative probabilities were 0.1, 0.3, 0.5, 0.7, 0.9 as the midpoints of those 5 areas. We want to find midpoints for n points in general. And for n points, this is the resulting formula. So I always like to double check things with an example. So if we take the first of the 5 points, we're saying n equals 5, and the first of the 5 points would be I equals 1. Then we have 2 times 1 minus 1 is 1. 2 times 5 is 10, so 1 divided by 10 is 0.1. And indeed, the cumulative probability of the first point was 0.1. Okay, let's do another one. The fourth point. 4 times 2 minus 1 is 7, divided by 10, 0.7. That's right. All right, so this is just a formula to figure out which cumulative probabilities we look at. And then we do the exact same thing as we did before. So I have this here listed, but it's the exact same thing what we did with 5 points. If I have a sample, I first order them, right? So I've standardized them, then I order them. And if I then want to check whether they are normal 0, 1, then if this is true, then the theoretical and the empirical quantiles should be approximately the same. The theoretical quantiles we can compute based on the normal 0, 1 distribution. The empirical quantiles are just our values z. So we plot them in a scatter plot, and if the distribution is really normal, then we get roughly the line y equals x. This is called the quantile-quantile plot, or qqplot, and it's used obviously to check the assumption of normality. Here's a simulated example. So I'm using simulated examples here because, well, otherwise you can blame it on strange things happening for any one data set. If the distribution is, if it's simulated, we know the distribution is normal and there's no two ways about it. So what you see here is a beautiful straight line. This is completely what is expected. If you have never seen plots like this, I've heard students who are reacting, well, but this isn't straight. Well, but it's not inconsistent with a straight line. I realize the points wiggle a little bit around, but it's not like there's a straight line going from down here going up to there. It's not like it's going into wild curves here that it follows some pattern. I mean, it goes a little below, a little above, a little below, a little above. This is a beautiful straight line that you can put on the wall and frame it and say, this is straight. Okay. Here's another simulated example. And we have another straight line. With justification, you can complain about these 3 points over here, right? So they're a little off the line, and I agree, they're off the line. These 3 points represent outliers with very large values, and they correspond to these values over here. So large outliers you see on the right, and small outliers you see on the left. When we evaluate qqplots, we concentrate on the center. At the very end, there is little probability, and it's more variable. You can detect outliers up here and down there. We concentrate on the core in the middle. And the middle is beautiful. This is a straight line. Good. So now a question for you. If the assumption of normality is not met, then one choice that we have is to transform the y variable, refit the model, and you get new residuals, and then try again. Is it better? So here we have a qqplot of one model, I forget which one it is, and then we have the log transformed model here. Now this is real data, it's not made up data, I think. So the question for you is, well, did one help? Are both terrible? Are both good? I will leave that for you to decide, and I'm moving on. Yeah, and that actually is the end because this is the beginning of the next segment.